We are up to, I guess this will be video number 10 in our series, Analytical Mechanics. The playlist for the analytical mechanics and all of the other subject matters is at the website, digital-university.org. Now, in our earlier videos, we'd established that if we have a spring and then we attach a weight to it that displaces the spring, say in the x direction, and a maximum displacement of a, that then the block here will go up and down with a natural frequency omega that is equal to the square root of the spring constant divided by the mass of that block. In those problems, though, we had ignored the mass of the spring, so we were assuming that the mass of the spring was so small compared to this mass that we could ignore it. And in fact, with most of the harmonic problems that we encounter in nature, and we're trying to simulate those problems with a spring system, indeed you can ignore the mass of the spring. So what we've derived in those earlier videos has a lot of practical applications. But suppose that the mass of the spring is so large that you cannot ignore the mass. Then, in that circumstance, what is the natural frequency of the system? And to solve that problem, which is rather a lengthy process, but we're going to give it our best effort here. To solve that problem, we're going to rely upon a lot of the background from video number 6, where we had considered the energy aspects of harmonic motion. And so now, here, for this video, if we have the block of mass m going up and down, then the kinetic energy of the system would be the kinetic energy of the block, which would be 1/2 m x dot squared, where of course x dot is dx dt, plus now the kinetic energy of the spring, where the spring has a total mass of ms. So the first question I guess we have to consider is, how do we determine what the kinetic energy of the spring is? So let's think of it like this. Here we have the spring. It has a natural length of L before it gets stretched out by the block that we attach to it. Suppose that we are at some distance from the top of the spring, small l, and we have a small differential of line element here. What would be the mass in this differential line element? Well, that would be equal to dl divided by the total length L times the total mass of the spring. The amount of mass that we have, let's say we were here at 1/3 the distance. The amount of mass, of course, would be just 1/3 the total mass of the spring. It's the fraction of this distance divided by L times the total mass is how much mass there is in that part of the spring. Well, in this part, dl, then, it's just dl divided by L times the total mass of the spring. Or we can think of this as, this is the density of the spring, ms divided by L. That times dl will be the amount of mass in that differential section there. Now, when we attach the block to it, and the bottom part of the spring gets displaced a distance x, how far does, and if we're here at a distance L from the top of the spring, how far does this point get displaced? So let's think about that for a moment. Suppose, for example, that we were right at the midpoint of the spring, at L/2. Then we attach the block to it, and the bottom part of the spring gets stretched out a distance x, then that midpoint is now going to be at L plus x divided by 2. Or the net displacement will be this minus this, which is just x over 2. So if the bottom part of the spring gets stretched out a distance x, the midpoint of the spring gets stretched out a distance of x over 2. And that probably seems intuitively obvious. What happens if we were, say, 1/3 the distance down, and then the bottom part of the spring gets stretched out by a distance x? So here we're at L over 3. Then when the bottom part gets stretched out a distance x, then this is going to be at L plus x over 3, or our 1/3 point gets displaced by x over 3. Well, let's say then we're at some distance small l. That could be our total length divided by, could be 1/5 the distance, or 1/9 the distance, or 7/8 the distance, whatever. That's just going to be capital L divided by y. Then when the bottom part of the spring gets stretched out that distance x, this will be at L plus x over y. Or its net displacement would be this minus this, x divided by y. But y, that is capital L divided by small l. So our net displacement is x divided by y, or that would be x times that reciprocal, small l over capital L. So if this stretches out a distance of x, then here when we were at L, that will now be at small l divided by capital L times that displacement at the bottom of the spring, x. Now let's ask this question. If we have a mass here, and this is going up and down at velocity x dot, what will be the velocity here going up and down? Well, that would just be the derivative, the time derivative of this. So let's just write that out. We are right here where we have amount of mass that's equal to this. So we have dl over L times this, and then the velocity of this point going up and down, if you're at the bottom of the spring it's going up and down with velocity x dot, then here it's going to be the derivative of its displacement over time, d dt of small l divided by capital L times x. That will be the velocity of this point going up and down. But of course that's just simply going to be this times x dot. So at this differential we know what its mass is, that's this, and we know what its velocity is, that's this. So the kinetic energy at here dl, that's going to be 1/2 the mass, that's this, times the velocity squared, that's this. So let's write this first. We will have L divided by capital L x dot squared, and then times the mass term, that's this, ms divided by L dl. So that would be the kinetic energy associated with this differential. But of course, we don't want to know just the differential kinetic energy. We want to determine what is the kinetic energy of the entire spring. So we'd have to add all these up by doing the integration. So we would say that the kinetic energy of the spring will equal an integral of all of this stuff. 1/2 ms over L times this squared, so that's small l squared, large L squared, x dot squared, dl, and we want to consider this over the entire length of the spring, and that goes from 0 to what? Now we have to remember it's like this. We have the mass m, and this is going up and down at some distance x. So that means that the length of the spring is always changing. So you probably won't see this in the textbooks, but we're going to say for the moment the upper limit is L, the natural length of the spring, plus or minus x. X is the amount of displacement from equilibrium. Let's say that here is the natural length of the spring, L. Then we add the mass to it. So now it's stretched out like this, a distance x, and this is going up a distance x and down a distance x. So the length of the spring keeps changing. So that's why we're saying L plus or minus x. So this is turning out to be a rather strange integral. But let's, for the moment, let's take our constants to the outside of the integral. Do that first. So we'll have the kinetic energy of the spring will equal its mass divided by capital L cubed. Here we have a 2, so this should be the mass of the spring divided by big L cubed. Then we have the integral, we're saying going from 0 to L plus or minus x. Then we have this x dot squared. Then we have small l squared dl. And this is dx dt. So it's a very strange integral. Now, to help us out with this, here's where we rely upon what we were considering in video number 6, where we said that the maximum kinetic energy of a system is equal to its maximum potential energy, at least for harmonic systems. Now, for the spring, it's not going to have a maximum kinetic energy unless this is at its maximum value. Let's remember what x dot is. We'll get back to this business later. Now x dot, of course, is the velocity of the block. So here we have this. And let's say this is the spring unstretched. And then here we have it with the block attached. And this block is moving up and down. And here's the equilibrium point, the block of mass m, moving up and down, and we designate its velocity as x dot. It's in the x direction. X dot is dx dt. Remember now, in video number 6, we determined that this mass will have its maximum velocity at this equilibrium point right here. That is where we have x dot maximum right here, whether the spring is going up to that equilibrium point or whether it's coming down to that equilibrium point. That is where the block has its maximum velocity. And again, we proved that in video number 6. And that then is when the length of the spring is L. So this helps us out in two ways. When the spring has its maximum kinetic energy equals its mass divided by L cubed, and then for the integral, that's going to be 0 to L, and this is a maximum value, and that maximum value for the velocity, that's just some number. And we can take that number to the outside. Right now we'll just say this: the maximum kinetic energy of the spring will equal x maximum dot squared L squared dl. And that occurs when the length of the spring is its natural length, capital L. You have L squared dl, and this maximum velocity for the block that's attached to the spring, that's just some number. So we can take this number to the outside of the integral. So now we have the maximum kinetic energy of the spring equals, oh, and we forgot something else. Let's go back up to here. Here we had a 1/2, so here we should have 2L cubed. And here this should be 2 times L cubed. So here we have now the maximum kinetic energy of the spring is going to be its mass divided by 2 times L cubed. The maximum velocity of the block, that's just some number that can go to the outside of the integral. Then we have times this integral from 0 to L, small L squared dl. And this is real simple. That's 1/3 L cubed, small L cubed, going from 0 to big L. So this equals 1/3 capital L cubed. So this integral is just 1/3 capital L cubed. So let's write this in place of this. One-third capital L cubed. So this cancels, this cancels. We have the maximum kinetic energy of the spring equals its mass divided by 3 times 2 is 6 times the maximum velocity squared of the block. Now, what is the maximum kinetic energy of the block? Well, that's real simple. The maximum kinetic energy of the block is just its mass, 1/2 its mass, times its maximum velocity, squared, x dot maximum squared. So the total maximum energy of our system is going to be this plus this. Let's see if we can squeeze that in down at the bottom here. The maximum kinetic energy will equal this plus this. It looks like we can factor out a 1/2 x dot squared, and then we should get our answer. We will have it that it will equal 1/2 x maximum dot squared times the mass of the block, m, plus the mass of the spring divided by 3. 3 times 2 is 6. So this is the maximum kinetic energy of our system. And we said a few moments ago that that has to equal the maximum potential energy of the system. Well, let's write this at the top of the board, and then we can discuss further the significance of this. So we have the maximum kinetic energy is this, which is going to reappear at the top of the board now. And again, what we want to do is set that equal to the maximum potential energy of our system. So, maximum kinetic energy that was equal to 1/2 x dot squared maximum, the maximum velocity of the block, times the mass of the block plus the mass of the spring divided by 3. Now, can we get an expression for this? Here we have it where our system is like this. Here's the block of mass m, and it's going up and down in the x direction. So the equation of motion for this, which we derived in our previous videos, would be x equals a times the sine of omega t, where a was our maximum displacement, or the amplitude of our system. Omega, that's the natural frequency of our system. Now, if we didn't have to take into account the mass of the spring, then of course omega is just the square root of the spring constant divided by the mass of the block. That's not what it is for this system, because we have to take into account the mass of the spring. But we can find out what x dot is, the velocity of the block, by taking the time derivative. So we'll have x dot will equal omega times a, omega a times the cosine of omega t. Again, just taking this time derivative. Now, what will be the maximum value for it? Of course, that's when the cosine just equals 1. So there's x maximum. We want it squared, so that's just this. So we can write this in terms of x dot maximum squared. So let's put that in there, omega squared a squared. This is omega squared a squared. So there is the maximum kinetic energy of the system, and we stated that that has to equal the maximum potential energy of the system. And in video number 6, we derived for our harmonic system, an expression for the potential energy. That was just 1/2 the spring constant times the displacement squared, x squared. So the maximum value that this can have is when x is at its maximum value, and that's just the amplitude, A. And again, in video number 6, we explained that this has to equal this. So we have this expression equals this expression. So we can get rid of this, and we have this equation. So the 1/2s cancel, the a squareds cancel, and we have our natural frequency squared will equal k divided by this. So we have omega squared equals k divided by the mass of the block plus the mass of the spring divided by 3. Or the natural frequency is just going to be the square root of that. So there's the expression for the natural frequency of our system. Now, if the mass of the spring is so small that we could ignore it, then of course we would have omega equals the square root of k over m. The mass of the block, which is what we've been using in all the other videos, we didn't have to consider the mass of the spring. But if the mass of the spring is large enough that we can't ignore it, then the natural frequency of our system takes on this value. Okay, that's it for this video. I'll come back and join us for the next video, and here we're going to consider a system where again we have just a single spring, but now there will be 2 masses attached to it, one at each end, and we'll consider the motion of this system.